In this video, I'm going to be talking about Taylor series. So a Taylor series is a way of expanding any function into a polynomial. And the way you do that is you start out with a point that you're going to expand around. In this case, I'm going to call that point A. And then you take the function itself and you find the value at point A. Then you find the derivative of that function in the value at point A, divide it by 1 factorial, which is just going to be 1. Then you take x and minus that. Then you take the second derivative at a over 2 factorial x minus a squared. Then you take the third derivative at a over 3 factorial x minus a to the third. And then you just do that forever. And then you have your function. So a Taylor series can be written as in summation form as I equals 0 to infinity f of a, the ith derivative of f, over I factorial x minus I to x minus a, sorry, to the ith power. I'm just going to be going over an example of a Taylor expansion series. So I'm going to expand the function sine of x around the point pi over 2. So we are going to end up with f of x is equal to, f of a, so we're going to have sine of pi over 2 plus f prime of a, so that's going to be cosine pi over 2 over 1 factorial x minus pi over 2 to the 1 plus the second derivative, so that's going to be negative sine pi over 2 over 2 factorial x minus pi over 2 to the second. The third derivative, so the derivative of this is going to be negative cosine pi over 2, 3 factorial x minus pi over 2 to the third. And then the fourth derivative, so the derivative of this is going to be sine pi over 2 over 4 factorial x minus pi over 2 to the fourth. And then this is the last one because I can't go on infinitely. The fifth derivative, so the derivative of this is going to be cosine of pi over 2 over 5 factorial x minus pi over 2 to the fifth. And then if you notice, pi over 2, the cosine of pi over 2 is 0, so this term is going to go away. This term is going to go away. This term is going to go away. So we end up with, and then the sine of pi over 2 is 1, so we're going to end up with 1 plus, and then if you notice, every other term is going to go away. So we're only going to have x to the 0, x squared, x to the fourth. So we're only going to have even powers of x. If you can notice the pattern, that's always going to be true because every other one's going to be cosine. So we have 1 minus 1 over 2 factorial x minus pi over 2 squared. And then if you notice also that we go sine, cosine, this gives us a negative, cosine, this gives us a positive, and it's going to keep going negative, positive, positive, negative, positive, negative. So we're going to be adding 1 over 4 factorial x minus pi over 2 to the fourth minus 1 over 6 factorial x minus pi over 2 to the sixth plus 1 over 8 factorial x minus pi over 2 to the 8th. And I didn't full on calculate these ones, but if you notice the pattern you're doing, this is what it's going to end up being. And so then I'm just going to show you what it looks like on a graph. So here you can see that I have sine of x in the GeoGebra, which is a free program you can use to graph stuff. In green, this is the sine of x. I'm going to be expanding it around 1, so that's why there's a point there. So if you just use the first term of the Taylor expansion, you just get a flat line. The second term, you get a line with a slope, at least. Third term, you get a parabola, so on and so forth. And you can see that each term you add, it gets closer and closer to, so this one right here is a function with x to the power of 4 in it, and you can see that it's getting pretty close. And if you skip all the way to polynomial with x to the 10, you can see from at least here until here, it's basically spot on. Then it goes a little bit crazy. That's why the when you're using estimates and stuff, the point of expansion is important, because you want, if you're using it to estimate a function, then you want to pick a point where you want the range to be. If you were to go on infinitely, this curve should match up exactly, but realistically, you can't go on infinitely. So that's just an example of what the graph of the Taylor adding different components to the Taylor expansion would do to the graph of a function. So I'm just going to run through another example. We have e to the x, and I'm going to expand around a is the natural log of 2, which is about 9.3, that mess. So we have f of x is going to be equal to, first we just have e to the natural log of 2 plus the derivative of that is going to be e to the natural log of 2 over 1 factorial x minus natural log of 2. Then the derivative of that is going to be e to the natural log of 2 factorial x minus the natural log of 2 squared plus e to the natural log of 2 over 3 factorial x minus the natural log of 2 to the third plus e to the natural log of 2 over 4 factorial x minus the natural log of 2 to the fourth. You can notice that e to the natural log of 2 is just 2, so we have 2 plus 2 over 1 x minus natural log of 2 plus 2 over 2 x minus the natural log of 2 squared plus 2 over 6, 3 factorial 6, x minus the natural log of 2 to the third. And you could probably see what's happening here. So we could write e to the natural log of e to the x, the expansion for e to the x centered around a is the natural log of 2 can be written as the infinite sum of, this is always going to be 2 over I factorial x minus the natural log of 2 to the I, where I starts at 0 and goes forever. So you're just going to have this dot 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 2 over 4 factorial, 2 over 5 factorial, 2 over 6 factorial, x minus the natural log of 2 to the 4, x to the minus natural log of 2 over to the fifth, so on and so forth. Here you can see in red, that's e to the x. This is the first term, which is just f of x equals 2, and here is the value that we are expanding upon. So if you add the second term, you get a linear. The third one, you can see it stays with the function longer, and then each term you add after that, you can see that it stays with the function. It more approximates the function for a longer amount of time. Here is with the fifth term, right? Here's with the sixth term. You can see that here it splits off there, and there it lasts a little bit longer. You can see even up here that the green, which is the older, which is the one without the sixth term onto it, diverges a little bit longer down the line. And then you can see when you do 10 terms out, you can see that this 10 terms out, which is in the orange, it stays with the original function much longer. And if you were to do this infinitely, it would be exactly on the function.